So I think it's appropriate, since we're talking about shear walls, that I tell you about a recent development for the last couple of years with one of my former students and current associate, Dr. Leopoldo Tesser from the University of Padova in Italy, to address the issue of two-dimensional response. Before I do that, I wanted to let you know that, of course, the fiber beam column element has been around for now a number of years, has received various contributions and refinements, as you heard also from Professor Lowe's. There is a set of publications, but it mainly addresses behavior in flexure and axial force, with some attempts to include shear as an uncoupled contribution. In parallel with this work, we have looked at a three-dimensional beam column element that includes 3D shear and torsion in the context of a fiber model that can be used in large-scale simulations. And so it seems to me, at least I would like to think that in the future, and by future I mean maybe in 3 to 4 to 5 years, once we are sure that these elements work robustly, that one can mix and match. So there can never be an issue, which is the one thing that bothers me about so much about the presentation that are going on, that we are going to model the entire 20, 50-story building with a single type of element. Instead, a platform like OpenSees should be geared towards mixing and matching of elements. You use elastic elements for portions of the building that are not important, and you use inelastic elements of various levels of refinement for the portions that you think are important. And of course, that importance evolved in the process of the simulations. You don't know beforehand, right? So in that context, of course, this is the important box that we fit in, and you all know about the methodology. I wanted to show you that shear walls, of course, have received recent prominence, and they don't come in plane configurations. They come in box configurations, L-shaped configurations, T-shaped configurations, as you heard from Professor Lowe's. And these kinds of configurations, when subjected to 3D response, undergo, depending on the size of the system, torsion and shear lag that renders at the critical sections the assumption of plane sections remaining plane a little invalid. And you saw the example of Professor Wallace's walls. So here you can see an outline of this shear wall that was used in this high-rise building, and you can see that basically the shapes are kind of complicated. They are not just plain walls. Moreover, we have a number of applications that do not fit the subject of buildings. We have bridges, box girder bridges, where we also want to be able to use some of these elements. And we have offshore platforms and all sorts of other things, which I'm showing here. So and nuclear power plants, not to forget that, which of course is not very popular in the United States in the current time. Anyway, so with Tesser, which is a portion, as I said, of the research, we have another part of the research that was completed, but it's not under OpenSees, so it doesn't fit the purposes of this excellent workshop that Frank was so kind to organize and peer to support. We will be porting it hopefully to OpenSees sometime in the future, but this is already available in OpenSees, at least not for everybody to use yet, because we're still writing the papers and calibrating and testing some of the robustness, but it is available, so in that sense it fits today's discussion. So we set out with Dr. Tesser to develop an element that addresses plane stress behavior and combination of plane stress and out of plane behavior. So as you saw, the title is shear walls and plates. Reinforced concrete plates, so we can simulate things like diaphragms if the need arises for some reason. And then, as you will see in these shear walls that I would like to show you, we of course have combined flexure out of plane and shear in plane. When the shape is a C-shaped wall, we have that. And then we need this kind of element. In any case, there has been an extensive set of investigations on the behavior of these elements, starting with some of the work in Zurich, 85, work in Toronto, work at Houston by Professor Su. This is by under Professor Collins and Vecchio. Stevens was their PhD student. And then there is some work recently also in connection with power plants that takes place in Japan, nuclear power plants, and many other places. And of course, NEES is also active in the area. So recent tests by nees, and here we are just including a few. Also significant amount of effort to understand the behavior of elements subjected to multi-axial state of stress. So the existing models can be divided into two kinds of categories. First, plane stress models, and then the so-called fiber beam models, even though that would be better stated as a beam model, and then the fiber is part of integration. Some of them are incorporated in commercial software, OpenSees being, of course, not a commercial software, but also there. And the plane stress FE models seem to have some issues of accuracy for general stress states, particularly computational efficiency and robustness issues. Some very successful elements are used in the commercial world, but certainly not for earthquake engineering applications of large scale, because they have a level of sophistication that renders them very expensive. On the other hand, fiber beam models with shear appear to be limited to cases with moderate demand, and I would like to add just 1D shear at best, right? And so here we're talking about some shear fiber beam column models that have been proposed starting from 1997, so they're already 15 years old, not yet available in OpenSees, unfortunately, but in the planar shear. Okay, so the current work aims to develop, so the current work meaning last year's work by Dr. Tesser aims to develop this efficient membrane and plate model. And the element should be general and suitable, accurate and computationally efficient, and we are using for the constitutive model, by the way, whether you use a fiber beam column element or a finite element, the thorny point is the constitutive relation. You need a 3D concrete model, and you are going to constrain the 3D concrete model to work in the plane, or in the plane of the plate, which means that one of the stresses will have to be constrained to be equal to 0. The out of plane of the plate stress. Anyway, so I'll talk a little bit about that. So this is a serious problem in constitutive modeling. And so people who have developed constitutive models for concrete dams, for example, have an easier time, in my view, than some of the people working in plates and walls, shear walls, particularly under cyclic loading, for this reason. All right. The membrane and plate model is implemented in a general purpose platform that is OpenSees. So all the work that I will be presenting is actually in OpenSees, and then I will tell you what Leopoldo did to get the results, which are pretty impressive. Okay, so experimental evidence under uniaxial response. So that at the top is the response of concrete in tension, at the bottom is the response of concrete in compression. We're going to put a plug on the so-called plastic damage model. So those of you who are familiar with the term, plasticity is a way of incorporating the classical plasticity theory, whether it is 1D or 3D or whatever. And then the damage is a way of reducing the stiffness, which of course the plasticity theory doesn't do. You combine the two in an interesting combination. So this is tension compression. And so essentially what you are trying to achieve is, and here we prepared this for an audience that is not quite as prepared as you, so we were trying to be kind of very clear. So basically this would be the initial elastic slope, and with damage you would get something like this reduction, right? And the residual strength that occurs as a result of this is basically what is described as damage, right? So this would be elastic response. This is what you observe on the envelope. That is a residual strength, and that kind of residual strength you can simulate with damage. And of course, damage in tension is different than damage in compression, so you need two scalar variables, and so on and so on. I don't want to belabor the point so late in the day. If you are interested, we have a paper that was published in a recent conference. I cannot be happy to send you, and I think it's very short though. And we have a couple of papers submitted to ACI that will be longer, assuming they get accepted. You're certainly welcome to have them once I hear that they have been accepted, which is not clear. All right, so in any case, the damage parameter is basically used to take this slope and reduce it as a percentage of the amount of the strain that has occurred. So you see the strain affects the amount of damage you observe. This scalar parameter evolves with loading. So this is a simple explanation of the damage idea. This is the residual strain coming from plasticity. You combine the residual strain from plasticity with the damage idea of reducing the stiffness, and you get what is known as a plastic damage model. You do that in 3D, and you have a 3D concrete plastic damage model. By the way, this is not original. It's only modification of work that was already published several years ago by Faria and Oliver. And so that is 2005, I think. So it's a well-publicized work, and they did it in the context of concrete dams, which is where a lot of this work takes place. And there it is in 3D model, as I mentioned earlier. All right. So you see, in this case, you implement it in the context of the residual strain, and that gives you the so-called plastic damage idea. So I think these are the only equations I have because I wanted to keep it simple. So the concrete plastic damage model, looking at some classic tests. Here is the response in tension of our model. This is the experimental response obtained by Palaratnam and Shah. This is the evolution of damage in terms of the slope. It looks pretty good. This is the response in compression, 1D. Again, this is the response by Sinha and Gerstle, and the experimental result dating back 40 years. And this is the sort of evolution of damage in terms of the average slope, unloading, reloading slope. By the way, the concrete damage models do not have any of these hysteretic behavior, at least not in the simplicity, which we don't care about, really, for the kinds of analysis we want to do. That sophistication is too expensive. All right? We are able to recover the crack width, which is important for some of the studies we do in sustainability and upgrading of facilities. So the correlation between average concrete and tensile strain, tensile damage parameter crack width can be derived from experimental measurements. And so we have a way of calibrating that. This correlation holds only for micro cracks. For the estimation of large crack widths, under seismic excitations, the reinforcing steel strain is what you need to use. So if you are talking about micro cracks, environmental loading, whatever, small things, then the idea of a damage parameter relation is quite useful, and we do that in structural durability studies that Dr. Tesser is conducting over in Europe. But if you want large crack widths under earthquakes, you have to use the strain in the reinforcing steel, and then you have to deal with some of the issues of localization and stuff like that for correct calibration. Okay. To simulate 2D and 3D conditions, stress conditions, you need a failure envelope. There are some classic tests which are almost also 40 years old, actually a little less, actually a little more, sorry. And we are able basically with our response to match the response of concrete under pure compression, compression and tension of different ratios. You see, this would be the ratio of 20% tension of the compression, the response in compression. So you use that for tension and compression states. We played a very important role. So to develop a membrane model for plane stress conditions, you need to constrain the constitutive relation to work in 2D. That constraint imposition works very well for metallic materials based on J2 plasticity, but it is very difficult for concrete of the kinds I described. And I'll be honest with you, I told Dr. Tesser, unless I see many large-scale simulations by all of you here, I would never be able to say I am confident that this model works robustly. You have to have 1,000 people use the model with only 2-3% failure of convergence to be able to say that the model is robust. And at the moment, we only have 15 simulations. So whatever I tell you today, you take it with a grain of salt, right? We succeeded in doing some interesting stuff, but until the day where all of you can use this model and tell me you are satisfied, there may pass 5 to 10 years, okay? But in any case, that's what we need to do. Otherwise, you know, we're just writing papers. So the 3D concrete law is constrained to a plane stress state. The reinforcing steel is an independent steel layer, which is isotropic. I can put as many reinforcing steel layers as I want, but that is a very simple problem because it's a layer. I do not account for bond Therefore, I assume full bond between concrete and steel, and I do not account for the dowel effect of the reinforcement, which means that there is perfect meshing of the two materials at this point. All right, we start simple. And only if we find that we are missing something, we add the extra features, which of course is the plan in the future. You will see where that comes. Okay, so this is the reinforced concrete with several layers of reinforcement. We are using the Menegotto-Pinto model from 1983 that I worked on as part of my PhD thesis, so you know how old I am. And OpenSees, of course, steel O2, otherwise known as steel O2 in OpenSees. We are doing for plates integration through the thickness in the form of layers. So we have to add a layer section model in OpenSees, which I think Dr. Tesser did. And then the reinforcing layers can be inserted in the various depths, and you know these are well-known stuff that you have to do. So we are using at this point about 7 layers to represent the distribution of strains through the depth of the concrete plate. Sorry. Okay. So here comes one that is one of my most important messages to my students when I work with them. I don't tolerate parameter tuning. One set of parameters, please. The best you can come up with. All the specimens with the same set of parameters. This doesn't mean, of course, that we're going to use the same parameters for 3 KSI concrete and 6 KSI concrete, but exactly as Professor Lowe's was doing, we're going to come up with a relation that says we're going to relate the concrete strength to this parameter in this way. And there won't be any secret things hiding under the table. All right? That is important. Otherwise, none of us can really follow what exactly is happening in the simulations, right? So, now, you will see. So, here, I wanted to show you a series of successes. So, that's, of course, a dubious proposition, right? Everybody will say, well, you know, that sounds a little too much to believe. And I don't blame you. That's the way I would treat it also, and that was the way I'm still treating it. So, in any case, we are pretty satisfied at the moment. As I said, for me, if in 5 years' time this model is widely available and you all get to use it and you all tell me that it works well, then I would be satisfied. Today, I'm not satisfied. Today, I'll get a paper maybe out of it. Okay? That's about the extent of it, right? Okay. So, these are simulation of panel tests by Mansour and Su, Cyclic. Please note that these panel tests induce a uniform stress state. So in fact, all what you are checking here is one integration point. That's all what you're doing. One integration point, right? Okay. So for 45% inclination of the reinforcement with the cyclic, whatever the details you can see in that study and also in the papers, there is a particular test. This is the comparison. We are able to simulate not only the overall response, which is shear stress, shear strain of the panel, but also the individual strains in the vertical, in the horizontal direction for the reinforcement, which they have measured, which very few people simulate or show. Very good. Okay. Then we go to a completely different test. The reinforcement now is 90 degrees relative to the edges of the panel, subjected to shear. You see what incredible change in the response from this state to this state. Okay? All right. This is obviously the easier one to simulate if you ask me. But the important thing again is that as we simulate the overall shear stress, shear strain, we are also simulating the vertical stress, the vertical strain, horizontal strain relation, normal stress, vertical strain. I think here there is a typo probably. This is horizontal stress, I suppose, or maybe they're both plotted against the vertical strain. I guess, yeah, vertical strain, horizontal strain, because in this case maybe there is only subjected to uniaxial stress conditions. I don't remember exactly how this works. Okay. So we are done with the SU panels. Those are a classical test. Many people also use the panels by Vecchio and Collins, which are classical, but the Vecchio and Collins panels are not cyclic. More recent, there have been some cyclic studies, but the best cyclic studies to our knowledge are the ones by Mansour and Su. Now, to be able to see whether we can really simulate the behavior of concrete in more complex stress states, in other words, not just one integration point, but an entire specimen, we used some of the classical tests that are now exactly 50 years old, which are basically a landmark in the history of reinforced concrete experimentation, the test by Walter and Leonard in Stuttgart in 1962, which is a series of tests of increasing span to depth ratio, which established the famous shear valley that you read about in concrete textbooks. And so this would be the response if you only considered flexure. This is the response in the presence of shear. The reduction that occurs for span to depth ratios below 6 for the simply supported beam is very interesting. And so we simulated these tests, and I wanted to show you that basically with a plastic damage model, what you get is a scalar damage parameter in tension and a scalar damage parameter in compression, which you can use to identify the total amount of damage. And you can create little plots like this, so it shows you here roughly what is the mesh discretization. That's not a very fine mesh. It's not bad, but it's not very fine for this particular specimen. And you can see that basically we are representing the cracking behavior, if that's what you call this, right? The extent of it, the compression strut here that's by coming down and so on, you represent it relatively well. The extent of this behavior, right? By contrast, the compression damage, as you see, is concentrated along this main strut that is coming down. This is the tension damage, this is a parameter, this is the compression damage parameter. These plots were prepared with GSID, which is a graphic software out of Barcelona, the Polytechnic University there, and the famous center that Professor Oñate is leading, using sensor results from OpenSees, right? So you write a sensor to output the stresses and the damage parameters out into a text file. You read the text file and the mesh into GSID. You prepare these plots. And you can also prepare animation. So I have a movie. If there is interest and time at the end, I may show it to you. All right. So these are the shear failure tests of Leonard and Walter. This is a longer span, and you can see here quite clearly that basically we have the characteristic response of concrete, which is a bunch of cracks normal to the axis of the beam and extending over most of the length, with the concentration of damage in concrete in compression down here, directly where the load is applied. And so a crushing phenomenon taking place here, as you can see from this damage parameter scale. All right. So we are relatively satisfied with these tests. And so then we escalated the complexity of the shear walls. Same model, same parameters, except for the fact that you need to specify, and you can read more about this in the papers, which parameters are specified, how they change. There's only one parameter that needs to be changed, and that is sort of the damage parameters, right? The evolution of those needs to be specified as based on the concrete strength. So these are panel tests by Meyer and Thürlimann, which involve eye-shaped walls, so walls with boundary elements, if you like. But of course, in Europe, they don't worry so much about seismic applications. So the tests are cyclic, surprising, 1985, in Switzerland. But the boundary elements are not reinforced as would be expected from a seismic zone. Okay, and so we are able, let's say, to simulate this with this representation of damage. And one of the things I asked Dr. Tesser to do is to make sure that in the papers we do explain what this really means. Because a bunch of nice colors sometimes, may not say all that much to somebody who sees it for the first time, and I am certainly one of those who sees it, only once a month or once every 15 weeks, and every time I have to scratch my head. What exactly does this thing say about the specimen, right? Okay. So after finishing the planar shear walls, by the way, these walls are planar in the sense that they are only loaded in one direction, which is probably 95% of the wall specimens available in databases, right? Very few people have the ability to do 3D testing. And I have yet to see many tests that involve a variation of the axial force. if that ever exists, right? And it does exist for a number of reasons that I won't go into. So these are planar walls. These are plates tested by McGregor in 1994 in Alberta. And here we represent a compressed layer at the top, the tension layer at the bottom. You can see the characteristic cracking patterns that form when the plates are supported on all four edges. The response under midspan deflection, relatively good. Of course, we always have difficulty with the uncracked and cracked stage. The numerical simulation is typically stiffer. It underestimates the pre-cracked stage and overestimates the uncracked stage because we don't have a way of really simulating that very accurately, but we don't care about it, so we don't want to spend any time resolving this problem, right? I was most interested in this part, so I can do simulations of failure. And then, and here comes the interesting part, U-shaped shear walls that have been tested with a mass at the top such and subjected to a loading regime that simulates what, in my opinion, is what a U-shaped shear wall will see in the field, which is response not in shear or shear, like most of the tests, but shear, shear, and torsion, right? Because no matter what you do to the building, is never going to be perfectly symmetric, particularly under inelastic action. So in any case, so they analyzed this particular specimen. These are the details of the loading. And here we have very, very satisfying results. And this is the one specimen that I wouldn't mind if we have, as I said, 2 minutes at the end. I show you the movie of what the simulation looks like, and you can see how we are tracking this response and how the state of damage into the wall looks like. And for this particular state, we have distributions of tensile damage over the wall, and we have some photographs that we can kind of look and say that we are sort of relatively close to the state of the actual specimen. Okay? So we continued. We looked at box shear walls as they are used in nuclear power plants. This has been tested by the Japan Nuclear Energy Safety Organization in 2006. This is a boxed shear wall. By the way, I forgot to mention, and you will see, I think you can see some of this here, these flanges are subjected to shear and out-of-plane bending, right? So essentially what you have here is a shell element. And I do buy the argument that this is an expensive analysis. I would never propose to use this kind of model in a 20-story building for all the elements in the building, right? But I may be interested in using this in the critical zones of the 20-story building. Let's be clear about it. Now, what exactly are we going to use to transfer the forces, torsion, shear, from a beam column element to that wall? That's another job, all right? Because we don't have those transfer elements, which are so essential, that's why all we can do right now is always simulate the whole building with the same element. Then we don't have to worry about transitions. But this is a poor man's modeling, if you allow me the expression. Just because we don't have, we pretend this is what we have to do. We don't, right? Okay. It's not a very smart modeling if you ask me, but anyway. All right. So, box-shaped shear wall, simulation of damage parameters, different states, information here about the cracking that happened in place, and indeed we have basically damages. You see here the wall was in a very stiff foundation, and so the actual damage actually occurred a little off the base of the wall. You see here there's just a little bit, almost like hard to quantify the number of, I guess it's probably related to the thickness of the wall, but somehow it's just a little bit off the base, and sort of the model in a smeared fashion, look at how few layers we have, represents more or less the same thing. All right. So in trying to keep things short, everything, as I said, sounds very positive. And believe me, we are very critical, and we try to do as nasty a job as we can, particularly me with the students. That's my job, I guess, in these kind of situations. But as far as I can see, this is a very, very, very promising element. I will be 100% convinced when this element finally gets to be used by anybody outside our group, and then people report success. Failing that, I keep repeating, it is just a scientific paper. Okay? Like 99% of what is out there. All right. So, we have simulated these different specimens. We are very satisfied with what we see. And we neglect the dowel action. So let me just emphasize some of this. We have simulated concrete cylinders, concrete prisms, RC panels, beam without reinforcement, planar U and box-shaped shear walls. All this stuff we simulated with the same constitutive model. The elements that we are using, by the way, for those of you who care, are a plane stress element, available in OpenSees, and the Mindlin plate element that is also available in OpenSees. So, the major contribution of Dr. Tesser is really the concrete constitutive model and some layers of reinforcing steel and stuff like that he inserted. Even though he also had his hand in improving some of the limitations of the Mindlin plate element, but that's a minor detail, right? So these are standard finite elements, right? Well known, which are available in OpenSees. All right, so the tensile and compressive damage parameters permit the interpretation of different experimental behaviors, such as structural damage, failure mechanism, tensile crack location orientation, micro cracks, concrete compression strut location orientation. As I said, I don't have the time to go into the details, and frankly, without Dr. Tesser here, I would probably be fooling you in telling you that from those color plots I can extract all this information. He probably can, and he always explains, whenever I put him under pressure, he always explains to me, I have to pass sometimes, all right? But the claim is that we can do all that, all right. We have neglected the dowel action and the bond slip of the reinforcing steel, which does not seem to affect the experimental data regarding strength. But unloading, reloading, discrepancies are evident in the tests I showed, even though I went very quickly through them. If you go through more details in the papers, you will see them. And we have identified where these two effects play a role. So it's not that we're just, right? So the dowel action is the more important, the more the orientation deviates from the principal straight directions. The robustness of the proposed RC membrane and plate model, remember these are two models, right? A plate and a membrane. So the plate is basically a shell because it includes membrane plus plate. The other one is pure in-plane behavior. Holds significant promise for its use as reliable tool for the simulation of structural systems under earthquake excitations. As I said, the proof still remains to be delivered when these elements are finally available for you to use. All right. Currently, we are working on bond slip and bond degradation because Dr. Tesser is involved in some durability studies. I don't want to talk about those. So here you can see actually the discrepancies, right? So with perfect bond, we get this. With reduced bond, we get this. And so we know what we have to do for some of these beams. Shear deficient columns is a very interesting challenge. They are slender, but the shear is significant in the sense of relative to their strength. They are not new columns, they are old columns. So we have some results for that. And I don't have anything to do with this because I raise my hands at this point. Some of Dr. Tesser's collaborators are also using masonry infield frames, the same model for masonry infield frames with a modification. That's there. I only wanted to show you that the context in which it is used for some of these masonry infield frames is really a very complex 3D context. So having such an element available with this level of in OpenSees, all of a sudden you can start doing some very interesting simulations. Of course, as I said, the accuracy of all these things still remains to be proven. So we are just at the start of what seems to be a very interesting path away from the beam column elements that have served us extremely well and will continue to do so, into beam column elements that include shear and torsion, which have yet to be delivered in OpenSees, to also plates and membrane elements in OpenSees for reinforced concrete that could potentially also use for masonry, if anybody is interested, if these Italian fellows succeed, right? And so here is some of the functions in OpenSees that Dr. Tesser added, just to show you only in this conclusion that he did some work in OpenSees and he inserted certain things there. Don't expect to see them in the near future because we are still evaluating this, right? So give me another year or two probably, and maybe if we are lucky we will succeed. So if I can have your patience, I will show you something that you can already almost imagine, I guess, from what I said, but I wanted to show you these this impressive AVI movie, which is this wall, which Dr. Tesser prepared, as I said, with OpenSees sensors and recorders, exporting the data into GSID, which then allows the preparation of this kind of animations. All right? Windows Media Player encountered a problem. Have you seen that with, so play again. So I guess you can see only part of it, right? In any case, you can see you can get the general idea. You can see how the flange walls really bend out of plane as they are loaded in shear, and how the damage evolves from the base of the wall to the other one. So there is post-processing capabilities. All you have to do is whether you can export some of the sensor and recorder data into something else that can help you interpret the results. All right, well, thank you so much for your attention. Sorry for being late in the day, but